Okay, today I will talk about an application of object detection and semantic segmentation in structure for motion mapping of historic mining sites, so many words in the title. I'm working in a interdisciplinary research project of the mining heritage in the Harz Mountains, and we are 4 people working part-time. Our archaeologist works for the state office. Then we have 1 historian working at the museum, which is 1 object of interest. And we are 2 people at the Institute of Mine Surveying of the Technical University in Clausthal. So what are our project tasks at the Technical University? First, the 3D reconstruction of parts of the historic mining system of Amitzberg. So that's the data set I will show you later as an example. There are 2 other tasks which are not relevant for this talk, but we have to reconstruct small-scale educational mining machinery models and some GIS analysis and so on. So the object of interest is the mine of Amitzberg, which dates back to 1150 in some parts and was in operation until 1980s. So here you see a mine plan from 1913, which is not the full extent. It grew even larger and faster in the later years and was converted to a museum in 1990. So the lower levels are all flooded and not accessible, but that's not a problem for us because we are just concentrating on this upper left part with a red rectangle, which dates back for 700 years. And this is the part we have reconstructed in 3D. So what were we using as a method? We used structure for motion underground with a DSLR camera and several flash units, and sometimes a GoPro on a long stick for parts we didn't want to crawl into. And we used terrestrial measurements using a total station or a Leica 3D disto for small confined spaces as well to get reference measurements and something to compare our structure for motion data to if we still in the right direction and scale. So the results from last year are this 3D reconstruction. We are still in the phase of dense matching and creating 3D models in high resolution, but this is the sparse point cloud you see. There are several 100 meters of tunnels and some water wheel chambers. We used Photoscan Pro, MeshLab, Cloud Compare, and Leica GeoOffice. And well, now we have 40,000 images of this mine with position in 3D and about 200 measured target points from 50 surveyed station points. So now I will come into the real topic today, the application of object detection and semantic segmentation. Here is an image of 1 water wheel chamber. This chamber is about 10 meters long, 5 meters high and wide. And on this face wall are several objects of interest. There are these metal bolting plates, which are a modern addition, but we use it as a test example for our object detection. There are sometimes boreholes from black powder blasting, which are more of interest for archaeologists, and there are tool marks. So the archaeologists wanted to have a look at this face wall and detect tool marks and some cavities where wooden constructions have been in former years to get an idea of what this room was used for during several periods. And to help it, we just played around as a side project with object detection. So the software I used in this case was TensorBox because I used it 3 years ago in another project and had a training data set already available. So I had at hand about 100 resized scaled images from different mines, ore mines, salt mines, whatever, with annotated bolting plates, and used this as a training data set and just applied this trained network on our new data set from this Amitzberg mine. This is one output of the object detection. So I used it as a black box. It's just a pre-trained network, and I adapted it with my training data set. And the output are these bounding boxes of detected objects, and it worked quite well first. But if you look closely, you see some false positives. In this case, these are our photogrammetric targets. These cards are quite similar to these bolting plates because they are rectangular and have a pointy thing in the middle. So we should adapt our training data set and put them into as a negative example where no bounding box should be detected. So you have this iteration, look at your data, where it doesn't work, adapt your training data set. And we have some undetected objects, which are not that big of a problem because we have many images of the same part. And if it's not detected in one image, it's probably detected in the next. So until now, you have just 2D bounding boxes in the images, but we want to get the 3D information. So it's a simple, fast approach. We took these bounding boxes and colored the images green at that point and used it as a texture and photoscan, projected and back. And you get something like on the right side, like a heat map, which is more green if all images of this part agree, yes, there's a bounding box. So it's really fast to apply without any complicated tools, and you see a visual representation of the spatial distribution of these objects. So we used a second simple approach to get 3D feature classes of these detected objects, and we just relied on the bundle file you get from this structure for motion. So you can export a bundle file in Photoscan or get it from Visual SFN and so on, where you have the 3D points and all 2D projections in the underlying images. And we just searched in the bounding boxes, whereas the next 2D point used directly this 3D coordinate to create a feature class and merged close lying points to get our 3D features. So the more correct approach wasn't implemented because it's a side project and we hadn't that much time. You could, of course, project these bounding boxes onto a mesh and get real coordinates of these four corners. So that's the object detection part. Here you see one part of the model consisting of 20,000 images with this green heat map texture applied. And there are some spots at these chambers where you see, okay, there are many bolting plates and some bolting plates in the tunnels and some false detections as well. But it worked quite nice, and we at least could use this as a tool for the real objects of interest. So the next step here would be to create a training data set of our boreholes and probably tool marks and adapt it. Retrain a network to detect these in 3D. The next part of my talk is about semantic segmentation, so pixel-wise labeling. The inspiration came from an archaeologist who said, okay, this is a nice face wall in this chamber, but I don't like these wire meshes. They obstruct the surface. Could we just remove them somehow? Well, yeah, we can try. So here you see an image. This is a stone of the face wall and these bolting plates, a nice smiling photogrammetric target and these wire meshes. So if you remove these wires in the image, you see just the face, and probably you could see more. So how to detect this? We first tested a simple geometric approach. Use the point cloud, create an averaging mesh, which probably lies between these wires and the stones, and filter it out, and it works, but just in areas where there's a mesh. In all other areas, it cut off the stones. So we had to segment our images into mesh parts and non-mesh parts. So why not directly classify each pixel, which is a wire? So we used semantic segmentation, took some inspiration from this UNED paper of biomedical image segmentation. They used pixel-wise labeling of cell borders and these in microscopic image. And these cell borders had quite an organic structure like our meshes, and they had the same problem. They just a very small training set because it's a tedious process to manually label all these images. So we had to label as well some images. We had 10 labeled images, so they are about 10 megapixel images, and 10 of these images are labeled by hand. You see a labeling on the right side. Ask my colleagues why we got not more data, but we have to make some data augmentation to really train our network on that. And for that, we extracted several patches of the input size of the neural network. So it has an input size of 500 times 500 pixels, and we have this 10 or 20 megapixel images, so we could extract many patches at many different resolutions and rotate these patches. What we could, as well as in this biomedical images, distort the images without creating problems for this specific data set. So here you see a patch of this wire mesh, and you see some random distortions of this image which were used for training because it's still valid in this case. And we trained our network in 2 or 3 days on a computer and came back, looked at the results. Okay, we have to put more negative data into where the image is just labeled black because there's definitely no wire mesh. And we trained it again. And you see here an original image and here the predicted labeling on this image. And another example, this is the original image. This is the labeling which got out of the trained network. And here you see one water view chamber as a textured 3D model, and the same model with the 1,500 predicted images as a texture. So if my archaeologist would be interested in this wire meshes, he probably would be very glad to have this, because he could see where the wire mesh lies on the model, but well, unfortunately he isn't. He wants to get rid of it. So we used this predicted images as a mask in PhotoScan. You can import masks to exclude parts of the images in the structural motion processing and dense matching. So we took all these 1,500 mask images into PhotoScan and processed the dense matching using this mask. So here you see an original image of this in this data set. This is the masked image as you see it in PhotoScan if you import the mask. And this is a generated depth map in the dense matching, where some parts are left out, and the resulting 3D point cloud without mesh parts, wire mesh parts. It's not a perfect result. We have still some errors from shadows of the wires and some problems in the dense matching. So it's not the perfect unobstructed surface we wanted to have, but at least it is a start. Here's a textured mesh of this part without the wires. So if you go back, this is an original image, and this is somehow an idea how it would look without this wire parts. So thank you for your attention.